Okay, now we come to something less serious. So I'll focus today on cities, and of course I don't need to convince you and this audience, the importance about, investigating cities. You all know, all these pros and cons of cities. Perhaps it's interesting to mention that perhaps before COVID, of course, we were concerned about cities, but we thought actually cities are there. We cannot change them too much. Okay, it's a sort of genetic endowment of cities. We can do, perturbative approaches to change here and there, but we never thought that we can actually change upside down cities. But actually during COVID, bad or good, we experienced different patterns of interactions, right? Okay, mostly negative, but sometimes also, with positive element. But I guess the positive element is we can think about a different pattern. And of course, this is difficult because these objects are complex evolving ecosystems, okay, definitely not stationary with a lot of feedback loops. We know about a lot of interactions. This is just a set of interactions, a subset of interactions connecting to the interaction between built environment and the green environment. And but in order to show, how these interactions are important, let me show you, a game we came up with, a game experiment actually. We came up with probably 10 years ago, okay? It's a video. There is audio, but it's not so important actually. So I can voice over. So you see, these are, at that time, actually, we had a collaboration with the Lego Foundation. So, our lab in Rome is now flooded with, I don't know, 500,000 of bricks, okay? So if you have ideas how to use them, please come. So at that time, we came up with this idea of letting people collectively construct a city. There is color codes. Each color corresponds to a different element of the city. It could be different jobs or constructions or residences or green areas. As you can see at some point, you see monitors in front of people. So people are working, but then while they work, actually, they see the outcome of their work. How good is the city with respect to a certain number of parameters of the city. And of course, that they look at this and they're trying to change the city in order to improve the city. Of course, they don't know, how to improve the city, okay? Because for instance, they have to improve the quality of life, for instance, but there is no brick for the quality of life. Now this, eventually became, an installation, going around in several exhibitions. In this case, the game is a one-player game. You have a mission. For instance, a mission could be the quality of life is low, can you improve it? And of course, you can only operate at this level. So you have basically 5 colors. You can actually change these elements, but still you want to have impact of quality of life, employment, and this kind of stuff, okay? But I can tell you, people are managing to do this. And now you're wondering, what is the feedback, right? Okay, the feedback is a mathematical model, which is underneath. Actually, it's an Hamiltonian model. And actually, through data, we basically infer this coupling parameter. So X, alpha and beta in this case, are socioeconomic factors, okay, that we basically get from the statistics office everywhere. But the important point is to infer the coupling parameters. And what is interesting in this case is normally an Hamiltonian is given by this, quadratic term, which would be the linear one, okay, if you're familiar with this. But what is interesting in this case, you have also a 3-body interaction. So which makes, the interactions less, intuitive, because you change A, presumably you update B, but then perhaps C, is getting worse. So, of course, all this is totally hidden for the players. Players don't know, how to do it, but still they manage to play. You see the fraction of victories while they play increases, okay? And of course, you can also estimate how difficult is the task, because, for instance, the task could be improving quality of life. And the difficulty in this case is measured as a function of the size of the phase space, so the space of the parameters you have to target with your moves, okay? And larger is the space, easier your task, and the other way around, okay? So this is just to tell you, how you can actually pin down these complex interactions in cities. Actually, we found out that you don't need to go to 4 legs interactions or 5 legs interaction. 3 is already enough. These have been inferred on cities from France, UK, and Italy. If you wish, there is this feedback loop between, the hidden model and the players. Of course, at that time, the notion of digital twins were not so fashionable. Of course, there were a few, built, but not so fashionable. In a way, as Alessandro Vespignani mentioned 2 days ago, digital twins are there even before, the name was invented. Okay, we have a rich agenda on this, but don't worry, I will not speak about everything. I will pick one specific example and go through this. And the example is the one of the proximity-based cities. So there is a lot of fuss now about 15-minute cities in particular. This is very fashionable. Okay, this comes. The name comes from Carlos Moreno in Paris. The consultant of Anne Hidalgo in Paris, but the concept is much older. And the idea is, okay, our cities is now optimized for time. So you need to minimize time to reach every possible destination in the city. I don't know if you're aware that there's this Marchetti constant. So this is basically the distance reached during commuting while the transportation systems improve. And you see, people are not, minimizing time, are basically keeping always the same budget time for traveling, and then they just reach further. Okay, so this, of course, is enlarging the size of cities, sprawling, and all the catastrophic features, right? So somehow the change of paradigm with the 15-minute city is actually that all the essential services, and I'll say more about what essential means, should be accessible, either by walking or biking, within 15 minutes. Okay, forget about 15. 15 is just a number. It could be any number. But the point is, I should be in proximity, okay? So the first question is, it seems cool, right? Okay, but the first question we asked is, okay, are 15-minute cities greener? So, in a sense, more sustainable. So, of course, this is not the thing we did, because first we needed to compute, how 15 minutes is a specific city. At that time, actually, there was no quantification for this. Then, meanwhile, there have been several. So, for instance, here you can see how the CO2 produced per capita actually decreases with the fraction of people in a city living in 15 minutes condition, okay? Which seems, okay, reasonable. This is at the level of the single city. I could also, at the level of the whole city, but actually you can actually go down at the level of sub-regions in a city. This is Tokyo, for instance, with a caveat about size. Of course, if you take, cities with the same sort of proximity time, and I'll tell you in a second what proximity time means, larger cities emit more. Anyway, there is a sort of scaling also in this case, as Luis knows very well. So basically what we did was, okay, how 15 minutes are cities presently? So we constructed this platform you can access freely. There are almost 10,000 cities you can explore. And the typical picture, okay, so we got the cover of Nature Cities just for bragging for this. But the typical picture, it's not really visible, but the typical picture you get is something like this. When it's blue, it means that people live in a 15-minute condition. When it's red, it's about 15 minutes. When it's white, of course, it's the interface. And probably it's not really visible, but actually you have also bars, vertical bars on each. Basically, we use hexagons, something like 100 meters side, so very granular. And the bars are basically the population residing in that hexagon. So if you have high bars, you would expect also blue colors, okay? But there are a lot of examples, not so much here, in other cities in which you have high bars totally red, which means a lot of people are basically in very bad conditions locally. And the other important element is, okay, you see a sort of radial distribution, so it's a sort of center which is well-defined, but also, it's very inhomogeneous the way in which people access opportunities. So it's not so much about mobility. Here it's really about having access to opportunities, which means also chances to, express yourself, as the Universal Declaration of Human Rights says. So this is, again, is another way to look at this. This is London. You can see, the central London is almost totally blue from that perspective. You can actually click on a specific point. You see this rather plot in which for each specific element in the basket of the 15-minute city, you can see how much you are 15. So the red circle is 15, and the two curves are basically bike and walking, okay? It's very heterogeneous. This is an infographic produced by Nature based on our data and classified for continents. So you see Europe is leading. Actually, 15-minute cities is a European concept, okay? Also, cities in Europe are very dense. but it's very heterogeneous. You see, I mean, in North America in particular, everything is red, and it would be really complex, I mean, to heal this situation. So this is a specific point. So it's not so much measuring how much globally a city is 15 minutes, but what is the fraction of population living in 15 minutes condition? Of course, you want to try to increase this. So here, for instance, you see the fraction of population living before a specific accessibility time, and this is the accessibility time. So this vertical line is 15 minutes. So you see there are cities like this one in which only, I don't know, 5% of the population lives in 15 minutes condition, and cities like Paris in which above 90% of people are in this condition. So you basically take these points and you make this other plot. So this is the fraction of population living in 15 minutes condition, and this is the average proximity time for the city. There is a beautiful pattern here, okay, from, let's say, good situation of accessibility to very bad situation for accessibility. And if you want to know more, actually, you can actually plot this in a different way, in which now the points correspond to cities, but the color corresponds to the Gini coefficient. So you see, as soon as you go down in the fraction of people living under 15 minutes condition, also the inequalities increase in terms of dishomogeneities in the distribution of accessibility. So what you can do to heal these inequalities? So we did something typically physicists do, which is a very simple model. Of course, we don't want to relocate people, okay, because this would trigger all sorts of problems. We decided to relocate POIs, so point of interest. So locations to be visited. So these are in Rome the ensemble of all the POIs we have. This is a mix of OpenStreetMap, Google Maps, and other databases, okay, because of course it's very heterogeneous. And then we simply did, okay, can we relocate these POIs in order to increase the fraction of people living in 15 minutes condition? Of course, I mean, taking advantage of the population distribution. So this is what happens, okay? You basically have a migration of POIs in the city, okay? A lot from the center, but not so much, not only from the center. And actually, you see at the end of the simulation, you get close to 90%. You can also run, I mean, of course, you can run all possible experiments like this. This is, for instance, an experiment in which we start from 0 and we add little by little POIs. You see, you get at the end to the same kind of structure. And now if you're wondering why this is heterogeneous, it's because the population density in Rome is heterogeneous. So this is more one-to-one with the population density locally. There are a lot of voids and empty areas in Rome. This is another animation in which you can actually move the bar, okay, and see how does it change the actual map of the 15 minutes if you actually increase, I mean, run this algorithm, okay? And the interesting observation out of this is a sort of improved Robin Hood. Because the point is, you don't want to deplete, I mean, city centers. You don't want to make the life of city centers, citizen, I mean, worst, okay? You want to improve, I mean, the accessibility for other people. And actually, typically, city centers are so abundant in POI, so even if you deplete a little bit, this does not decrease the average accessibility time. And this is just to tell you, I mean, while in some cases it's really hopeless, I mean, to try to relocate POIs. I mean, look at this. So this is Atlanta, San Antonio, Dallas, Detroit, sorry for the US, but this is what it is. So you have to relocate, I mean, up to 80% of the POIs. Even this would not be enough to have a large fraction. So as you can imagine, I mean, what I'm saying is 15-minute city was an interesting concept, okay, just to think in a different way, but it's not the end of the story. It actually works quite well if the density is very high for compact cities, but out of this, intermediate areas, rural areas, which of course are important, okay, because part of the 55% of the population is not living in the center, actually it's living in the outskirts, it's not this. So this is more or less I mean, what we got so far. But of course, there is much more than this. So 15 minutes is, okay, it's not good for many, three, okay. It's not 15, gosh. It's not good for many other reasons. For once, actually, you only optimize for time, okay, but never for the value. So if I have an hospital at 2 minutes, which I know, I mean, the service is not very good. Typically, I take my car and I go somewhere else, right? Okay, so the value is not taken into account in this picture. Second point, I mean, you cannot have, I don't know, the Tour Eiffel in all possible neighborhoods in the city, right? Okay, so big landmarks cannot be accessible by walking or biking in 15 minutes, okay? All the other things, yes, but not the big landmarks. So you need another paradigm. So we went for it. And somehow, I mean, the point here is to try to optimize the number of opportunities reachable by people, not only by biking or walking. So, of course, biking or walking, if this is accessible, if this is far, I should have the opportunity to go as fast as possible also. So this also includes the transportation system. At this amount, this would be a long conversation, but perhaps we can do this later. I mean, there is an interplay between participation and representation, which has been discussed, I mean, thoroughly in this conference. Because of course I have a sort of hierarchy of cities. 1 minute city is really something, I mean, very local, in which local communities can decide by themselves. But also if you look at stadiums and cathedrals, subways, this is not something, I mean, we can decide at the local level. Okay, so this will be one point. So for instance, this is just now the color is proportional to the number of opportunities reachable by a person in that specific spot. And this is Rome, but we can do this for many cities. And if you know a little bit Rome, I mean, the highest color, the brightest color correspond to the metro lines. So you see how important the infrastructures are for this system. The last point, actually, but I go very quickly. Once you have this, you can also compute, I mean, how much POIs are accessible by public transportation or private cars. You can actually look for the interplay, so I don't go for the details, but this is for sort of car dependency index. So how much you depend on cars if you live in a specific point of the city. You see, city centers typically do not depend on cars. And okay, this is also in this case, there are a lot of heterogeneities. But the key point, most of the present cities heavily depend on car with strong heterogeneities, but with sort of, I mean, this kind of indexes could be used in order to think about policies for this. If you want to charge person who don't need actually car, I mean, this is one way to do it. Okay, but there are many possible ways. And of course, the important point here is not to create policies, but to give the impression of what could be the possible outcome of a certain policy. Okay, so this is the last slide. So I guess it's clear to everyone that we cannot have one-fits-all solution for all cities, right? I mean, they are too heterogeneous. You have to deep dive, actually, in each city and try to find solutions. There could be patterns, okay? But of course, the specific solution depends on city. Again, 15-minute city does not work for everywhere, actually, only for dense and compact areas. Probably maximizing opportunities and values could be one way. But more generally, and the three last points are more general, let me start with the second last one. So when we discuss about smart cities, of course, this is important. I'm pretty sure infrastructure are quite important, but to me, they are enablers. I mean, this is not the whole point. Okay, we cannot be saved by technology per se, so we need to put something else on top of it, especially AI, which for the time being is not enough, I mean, to solve these problems. So we need scenarios, sort of what-if machines, and I guess many of them are being presented also in these days. And as Alessandro Espignani mentioned, we need to couple all these what-if machines. We need to get a consensus, I mean, model in order to say what is the most likely outcome of a given action. Okay, then the politician will decide by themselves. And I guess, I mean, many people, I mean, mentioned, I mean, new forms of participation and representation. So this interplay, we can do, I mean, participatory budgeting projects at a small scale, okay, but can we scale up this, I mean, at larger sizes? I guess for this, we need to couple with what-if scenarios. And I stop here. Thanks a lot for the invitation.
Thank you, Vittorio.